Now we're going to look at complete bipartite graphs denoted by K sub m comma n. And these are graphs that are bipartite, so they have two sets of vertices that are completely different, and the subscripts on the complete bipartite graph denote the number of vertices in each of those sets. So the first set of vertices has m many vertices in it, and the second set has n many vertices in it. And we still have the property that none of the vertices in the first set are connected by any edges, and none of the vertices in the second set are connected by any edges. But what makes this bipartite graph complete is that, in fact, each vertex in the first set is connected to every vertex in the second set by an edge, and vice versa. So let's look at some examples. So the first example we will look at is K2, 3, where the first set of vertices has 2 vertices in it, and the second set has 3 vertices in it. And notice that each vertex in the first set is not connected by any edges, but they are connected to every vertex in the second set. And similarly, each vertex in the second set is not connected to any other vertex in that set, but is connected to each vertex in the first set. Can also look at the complete bipartite graph K33, K35, or K26. So notice that they are unique depending on just the number of vertices in each of the sets. Now we want to look at applications of bipartite graphs. So what makes these types of graphs so special? They're very useful to model particular applications, such as matching one set of elements to another set. So for example, we may want to assign individuals certain tasks or jobs within a workplace. And so we wouldn't want to match corresponding employees together. We would simply want to match themselves with each of the jobs they are trained to do. And similarly, we wouldn't want to connect any of the jobs together. We simply want to connect 2 vertices if one individual is trained to do that job. So in this way, we form a bipartite graph, since each vertex representing an individual would be one set of vertices, and each vertex representing the jobs would be another set of vertices. We'd simply draw edges between an individual and a job if that individual was qualified for that job. It is unlikely that this type of bipartite graph would be complete, because it's unlikely that you would have a set of employees who are all trained to do every single job within the company. It makes much more sense to have individuals specialize in particular jobs and have those responsibilities and spread the workload out. Now we're going to look at forming new graphs from old graphs. So we're going to define subgraphs. So a subgraph of a graph G, which has a vertex set capital V and an edge set capital E. So a subgraph of this graph is another graph with a vertex set W and edge set F, so that this graph simply contains some or maybe all of the vertices of the original graph and some or maybe all of the edges of that graph. So in the case that it does not contain either all the vertices or all the edges or both, it will be a proper subgraph. So H will be a proper subgraph of G if it's not equal to G. And so here's an example of the graph K5, so the complete graph with 5 vertices and a subgraph. So notice that we take a subcollection of the vertices of this complete graph K5 and a subcollection of the edges joining them. So notice that even though we take all of these vertices, we don't necessarily take all of the edges connecting them. So notice, for example, the edge EC is not within this subgraph, even though there is an edge joining these two in the original graph. In the case that we do want to contain all of the edges of all the vertices that we choose, then this particular type of subgraph is called a subgraph induced by a subset W of the vertex set V. So in that case, the subgraph induced from a subset of the vertex set takes all edges adjacent with all vertices in this set W. So, for example, we take an edge if and only if both endpoints are in W. So in that case, we would add this edge to this subgraph because it's an edge within the original graph and both of these vertices are here. We, however, cannot add the edge joining E to D, for example, because D is not a member of this set of vertices. Okay, so that brings us to all the simple types of graphs that we can define so far. Next, we'll look at various other applications and start to look at some algorithms defined on graphs as well.